Two galaxies are crashing together in a spectacular dance of destruction and creation. This is the Antennae Galaxies, a cosmic train wreck unfolding over millions of years. Within its beautiful chaos lie 30 strange phenomena that defy our current understanding of the universe. By the end of this journey, you will know the deepest cosmic secrets locked within this collision. We will uncover why black holes glow with impossible light, and where ghostly echoes of ancient stars still linger. What do you think is the most profound mystery the universe is hiding? The first mystery is a light that burns with impossible fury. Scattered throughout the Antennae Galaxies are objects so brilliant in X-ray light that they defy every known rule. Astronomers call them Ultra-Luminous X Ray Sources, or ULXs for short. Imagine a single cosmic beacon shining hundreds, even thousands of times brighter than any typical black hole should. That is the scale of this puzzle. According to our best models, a stellar black hole, the kind formed from a collapsed star, simply cannot feed on matter fast enough to glow this intensely. It would be like trying to force a garden hose to pour out the volume of a fire hydrant. The physics just does not allow it. So what are these things? One compelling theory points to the existence of intermediate mass black holes, cosmic entities that are much heavier than their stellar cousins, but smaller than the supermassive giants at the centers of galaxies. These middleweight monsters could potentially devour enough gas to produce such a staggering X-ray output. Another possibility is that we are seeing exotic and unstable accretion physics in action, where matter does not fall onto the black hole in a steady stream, but in a violent, chaotic frenzy that supercharges its brightness. The Antennae Galaxies are the perfect hunting ground for these enigmatic objects. This colossal collision is a cosmic pressure cooker, triggering rampant waves of star birth. All that newborn starlight and subsequent stellar death creates a rich soup of gas and dust, providing an all-you-can-eat buffet for any hungry black holes lurking in the chaos. Each ultra-luminous source we find is a direct challenge to our understanding of how black holes grow and how they consume the universe around them. They are brilliant anomalies, forcing us to question if our rulebook for cosmic physics is fundamentally incomplete. These brilliant anomalies are not the only spectacle forged in the chaos. The galactic wreckage is also giving birth to stellar cities of staggering scale. Within the tangled hearts of the antennae, astronomers have identified vast, dense collections of young stars known as superstar clusters. These are not your average star nurseries. Each one is a colossal metropolis of stars, often packing the equivalent mass of 1 million suns into a region that would feel cramped in our own galactic neighborhood. To stand within one would mean a sky perpetually ablaze, with stars so numerous and close they would outshine our own moon. The sheer density is almost incomprehensible, a cosmic New York City built from suns instead of skyscrapers. And the strangeness lies not just in their immense size, but in their very existence and potential fate. We are witnessing the rapid, violent construction of what might become the ancient globular clusters we see orbiting older, quieter galaxies today. These are the potential ancestors of those ancient, glittering balls of stars, but they are being assembled in a frantic rush over just a few million years, a mere blink in cosmic time. The collision provides the ultimate pressure, forcing immense clouds of gas and dust to collapse under their own gravity all at once, sparking a firestorm of star formation on an industrial scale. But will these glittering new cities survive, or are they doomed from the start? The gravitational tides within the colliding galaxies are immense and chaotic. Many of these superstar clusters may not remain bound together. They could be ripped apart, their stellar populations scattered across the merged galaxy, becoming a foundational generation of stars for a new galactic empire. Others, the most massive and densely packed, might just hold on, surviving to become those ancient globular clusters we see elsewhere. living fossils that tell the story of a violent, creative collision billions of years in their past. Their fate is a cosmic toss-up, a reminder that even in creation, there is no guarantee of permanence. Stretching far beyond the colliding hearts of these galaxies are the very features that give them their name. Two immense, sweeping arcs of cosmic material flow outward, resembling the delicate antennae of some colossal insect. These are the tidal tails, and they are anything but solid. Each one is a vast, streaming river of gas, dust, and orphaned stars, pulled out into the void by the immense gravitational forces of the collision. Think of it like this: when two galaxies swing past each other, their gravity does not just tug on each other as a whole. It creates a differential pull, a stretch, much like the Moon's gravity pulling more strongly on the side of Earth facing it, creating our ocean tides. But on a galactic scale, this effect is catastrophic and beautiful. The outer regions of the galaxies, feeling the weakest gravitational bond, a RE Chinese letter pulled away, drawn out into these long, graceful streamers. The sheer scale is difficult to grasp. These tidal tails are not mere wisps. They are structures that stretch for hundreds of thousands of light years. If you could stand at the base of one, its end would be lost in the darkness of intergalactic space, a river of suns and nebulae flowing into nothingness. But within their faint glow lies a profound strangeness. These tails are more than just debris. They are a fossil record of the entire galactic encounter. By studying the motion and composition of the stars within them, astronomers can rewind the cosmic clock. They can trace back the paths of these exiled stars to pinpoint the exact moment of the closest pass, calculating the original speeds and angles of the two galaxies involved. It is like finding a long, unrolled scroll that details the entire history of the collision, written in the language of starlight and hydrogen gas. These ghostly antennae are not just a namesake feature. They are the enduring signature of a gravitational dance that began millions of years ago. This frantic construction of stars comes with a predictable yet staggering cost. The Antennae Galaxies are experiencing a supernova epidemic. These colossal explosions, the violent deaths of massive stars, are occurring at a rate far beyond what we see in calmer galaxies like our own Milky Way. It is a direct consequence of the collision, a natural byproduct of creating so many massive stars in such a short time. When you build stellar metropolises at a breakneck pace, you also create an entire generation of stars destined to die young and die spectacularly. Think of it as a cosmic boom and bust cycle on an unimaginable scale. The collision triggers a star-forming boom, and just a few million years later, that boom is followed by a devastating bust of supernova. The sky within these galaxies must be a constant, silent fireworks display, with new stars flashing into existence only to be torn apart in blinding detonations a short cosmic moment later. But the true strangeness of this supernova surplus is not just the destruction, it is what that destruction creates. Each of these titanic explosions is a cosmic forge. Within their unimaginable pressures and temperatures, the very elements of life are cooked into existence. Hydrogen and helium fuse into heavier elements like carbon and oxygen, and those in turn fuse into even heavier metals like iron, gold, and uranium. This stellar shrapnel, this enriched gas and dust, is then blasted out into the surrounding space, seeding the galactic environment. The Antennae Galaxies are essentially undergoing rapid, forced chemical enrichment. In a relatively short period, they are being flooded with the raw materials needed to form rocky planets, complex molecules, and perhaps even life itself. A process that might take a normal galaxy billions of years to accomplish is being compressed into a frantic, chaotic few million years within this collision. This means the future planets that form from this enriched debris will be born into a universe rich with possibility. Their very composition forged in the hearts of dying stars and scattered by these relentless explosions. The galaxies are not just being reshaped, They are being fundamentally remade on an elemental level. But all this visible chaos, the exploding stars and swirling gas, might only be half the story. There is an invisible actor on this stage, a ghostly presence that holds the entire cosmic performance together, dark matter. We cannot see it, we cannot touch it, yet we know it is there because of its immense gravitational pull on everything we can see. Every galaxy, including our own, is thought to be embedded within a vast, spherical halo of this mysterious substance. In a normal, undisturbed galaxy, this dark matter halo and the visible galaxy at its center are neatly aligned, like a marble set inside a clear, oversized ball. But the Antennae Galaxies are anything but normal. This violent collision provides a rare and crucial test, because dark matter behaves in a fundamentally different way from the stars and gas we see. Normal matter interacts, it smashes together, it feels friction and pressure, slowing down and piling up in the galactic centers. Dark matter, on the other hand, is thought to mostly just pass right through itself and everything else, feeling only gravity's pull. So when two galaxies collide, a strange separation is predicted to occur. The visible matter, the gas and stars, should get caught in a cosmic traffic jam, slowed and concentrated at the heart of the impact. But the dark matter halos, largely unaffected by this drag, should keep moving, overshooting the visible wreckage. This would mean the center of mass for the entire system, the true gravitational anchor point dictated by dark matter, might not be where the brightest light shines. It could be offset, a ghostly center of gravity drifting away from the visible one. Studying this requires a cosmic trick, a phenomenon called gravitational lensing. The immense mass of the dark matter halo warps the fabric of space-time around it, acting like a giant lens. When light from more distant galaxies passes through this warped space, its path is bent, distorting and magnifying the images of those background galaxies. By meticulously mapping these subtle distortions, astronomers can essentially trace the invisible distribution of mass, painting a picture of the dark matter halo. In the antennae, early studies suggest this is exactly what is happening. The dark matter does appear to be behaving differently, its distribution potentially offset from the brilliant chaos of the colliding gas clouds. This makes the Antennae Galaxies a unique natural laboratory. We are not just watching two collections of stars crash. We are witnessing a profound separation between the visible universe and the invisible one that governs it. Each distorted image of a background galaxy is a data point, helping us map the ghostly anatomy of dark matter itself, forcing us to understand the true, hidden skeleton upon which the visible cosmos is built. This hidden fuel is the very lifeblood of the galaxy, vast clouds of cold molecular gas drifting in the darkness. Throughout the tangled wreckage of the antennae, astronomers have mapped immense reservoirs of this raw material, the hydrogen and other molecules that will eventually collapse to form new stars. But its distribution is what makes it so strange. In a normal, undisturbed spiral galaxy like our Milky Way, this gas is spread relatively thin, organized into graceful spiral arms. Here, it is a chaotic, overstuffed warehouse. The density and concentration of this molecular gas are far greater than anything found in an isolated galaxy. And it is this shocking abundance that powers the entire spectacle. The collision itself is the reason. As the two galaxies graze and merge, their immense gravitational forces act like a pair of cosmic hands, violently squeezing these vast clouds. This compression is not gentle. It is a shockwave traveling through the interstellar medium, forcing the gas into incredibly dense knots and filaments. Where once a cloud might have drifted for eons in a quiet equilibrium, it is now suddenly and brutally crushed, pushing it over a critical threshold. The cloud's own gravity, now amplified by this external pressure, can no longer be resisted. It begins to collapse, fragmenting into countless cores, each one a potential new sun. This is how you build a stellar nursery of epic proportions. The entire central region of the antennae has become a single, frantic maternity ward for stars, operating at a fever pitch unseen in calmer galactic neighborhoods. It is a direct, violent chain of cause and effect. The galactic collision compresses the gas, the compressed gas collapses into stars, and those stars, in turn, light up the chaos with their brilliant, short lives. This prolific gas is the hidden engine, the stockpile of cosmic lumber that is being used to construct entire cities of stars right before our eyes. Without this deep and strangely distributed reservoir, the firestorm of creation would simply flicker out. Amidst the visible firestorm of starlight, the Antennae Galaxies broadcast a different kind of signal entirely. Vast, invisible structures known as radio lobes unfurl from the galactic cores, pouring out immense amounts of energy in the form of radio waves. This is not the gentle glow of starlight, but the raw scream of electrons hurtling through powerful magnetic fields at nearly the speed of light. The process is called synchrotron radiation, and it paints a picture of extreme violence. Imagine forcing a subatomic particle through a microscopic, spiraling racetrack, its path bent by invisible magnetic rails. Each sharp turn forces the electron to shed energy, emitting a radio photon in the process. In a normal galaxy, such emissions might be localized, coming from the remnants of a single supernova. Here, however, the radio lobes are intense, widespread, and structurally complex. Their sheer power and strange formations are a direct testament to the merger's chaotic influence. The galactic cores, likely housing supermassive black holes, are being fed enormous amounts of gas and dust stirred up by the collision. This frantic feeding can ignite the engines of active galactic nuclei, launching jets of charged particles that inflate these colossal radio-emitting bubbles. But the signal is not clean. The radio map is a messy overlay, a cacophony where the roar from the central black holes blends with the collective blast of thousands of supernova remnants scattered throughout the star-forming frenzy. This tangled radio signature is the ghostly echo of the merger's power, a permanent record of electrons accelerated in cosmic cataclysms, their faint radio whispers telling a story of violence that our eyes alone could never see. Even the most brilliant stars in this chaotic nursery are not stable. Among the superstar clusters and supernova factories, there exists a class of stars so volatile they defy any sense of cosmic predictability. These are the luminous blue variables, stellar titans living on the very edge of stability. They are the rock stars of the cosmos, brilliant, massive, and prone to spectacular, self-destructive outbursts. Their existence alone is a rarity, but in the Antennae Galaxies, the collision has created the perfect conditions to breed them in unusual numbers. Imagine a star so colossal that its own gravity is barely able to hold it together. The outward pressure from its furious nuclear fusion battles constantly against the immense inward pull of its own mass. This precarious balance is what defines a luminous blue variable. They do not simply shine, they seethe and convulse. Their strangeness lies in their wild unpredictability. For years, even decades, such a star might burn with a steady, intense blue-white light. Then, without clear warning, it can undergo a giant eruption. It violently expels a huge portion of its own outer layers into space, casting off a shell of gas and dust that could contain the mass of several of our own suns. During these eruptions, the star's brightness can fluctuate wildly, and its temperature plummets as it temporarily disguises itself as a cooler, hyper-giant star. These are not the final, suicidal explosions of a supernova, but rather massive, recurring temper tantrums. Each outburst strips the star down, shedding its outer skin and revealing deeper, hotter layers underneath before the cycle begins anew. This behavior presents a direct challenge to our models of stellar evolution. We struggle to pinpoint exactly where these volatile giants fit in the life cycle of the most massive stars. Are they a brief, turbulent phase right before they die as supernova? Or are they a distinct type of stellar object altogether? Their violent mass loss is so extreme it completely alters their own fate and the environment around them. In the antennae, these stellar behemoths are contributing to the galactic pollution in real time, seeding the surrounding gas clouds with heavy elements and shaping the nebulae from which the next generation of stars will be born. They are living proof that even the fundamental rules governing a star's life can be broken, especially when born from the beautiful violence of a galactic collision. Even the dust between the stars seems to be alive with hidden complexity. As our telescopes peer into the chaos of the Antennae Galaxies in infrared light, they detect a set of spectral lines that form a strange, unmistakable signature. Astronomers call these the unidentified infrared emission features, a name that perfectly captures their mysterious nature. These are not the clean lines of simple gases, but a broad, complex set of wavelengths that together create a ghostly glow across the wreckage. For a long time, their source was one of the great puzzles of interstellar chemistry. The leading suspect today is a family of complex organic molecules known as polycyclic aromatic hydrocarbons, or PAHs for short. Imagine the basic structure of soot, those tiny flakes you find in a candle's flame. Now, picture that soot molecule as a miniature, flat sheet of interconnected carbon rings, with hydrogen atoms fringing the edges. That is the essence of a PAH, a sturdy, plate-like molecule that is surprisingly resilient. When a single photon of starlight strikes one of these molecules, it begins to vibrate intensely, like a tiny tuning fork being struck, and it releases that energy as a very specific set of infrared wavelengths. This collective shimmer from countless trillions of these molecules is what creates the mysterious infrared glow we detect from millions of light years away. But the exact identity of the molecules producing this signal remains a topic of intense debate. Are we seeing a specific, dominant type of PAH, or a vast and diverse zoo of related carbon-based compounds? The spectral lines are a bit blurry, a composite of many different contributors, making their precise chemical recipe difficult to pin down. This ambiguity is what keeps the unidentified in their name. Their sheer abundance in the antennae is another layer of the mystery. This is a region of immense violence, blasted by intense radiation from newborn stars and shockwaves from frequent supernova. Such a harsh environment should be tearing fragile molecules apart. Yet, the infrared features are bright and widespread, suggesting these PAHs are not just surviving, they are thriving. It appears the galactic collision itself is the ultimate factory. The same supernova that unleash destructive forces are also forging heavy elements like carbon in their hearts and scattering them into the surrounding gas. This provides the raw ingredient. The turbulent pressure from the merger then seems to efficiently assemble these carbon atoms into the complex pH structures, perhaps on the surfaces of dust grains, faster than the rampant radiation can destroy them. This means the very chaos that threatens life's delicate chemistry might also be actively manufacturing its most fundamental building blocks. These unidentified infrared features are more than just a chemical curiosity. They are a potential reservoir, a cosmic stockpile of the organic materials that, on a more hospitable world like Earth, could have been the starting point for biochemistry. Within the beautiful destruction of the Antennae Galaxies, we may be witnessing the widespread seeding of the very ingredients that make life possible. This hunt for missing cosmic giants leads us to one of the most persistent and puzzling gaps in our knowledge. Astronomers have long predicted that the superstar clusters of the antennae should be the perfect nurseries for a specific class of black hole, one that bridges the gap between the small and the supermassive. We call these intermediate mass black holes, objects with the mass of thousands, even hundreds of thousands of suns. Their existence seems logical. In the incredible density of a superstar cluster, with stars packed so tightly they nearly touch, stellar mass black holes should sink to the center, merge, and feast on the surrounding stars, growing into these middleweight monsters. Yet, for all the theoretical predictions, finding one here has proven incredibly difficult. They are the cosmic missing link, the ghosts in the machine. The strangeness lies in their elusiveness. This collision is the ultimate pressure cooker, creating the exact dense, chaotic environments where our models say these objects must form. So why can we not see them? The challenge is one of detection. A stellar mass black hole betrays its presence by pulling gas from a companion star, heating it until it glows in X-rays. A supermassive black hole at a galaxy's core dominates its surroundings with immense gravity and light. But an intermediate mass black hole, if it is floating alone in the core of a star cluster, has no steady food source. It might only light up during a rare, sporadic meal, like a single star wandering too close. Such an event would be brief and easy to miss. Other clues are subtler. You might look for stars orbiting an invisible, massive point at the heart of a superstar cluster, moving at speeds that defy explanation. Or you might listen for the faint, telltale ripples in space-time from a merger between two of these objects. So far, the evidence in the antennae remains ambiguous, a collection of tantalizing hints and frustrating dead ends. This is more than just a failed hunt. It is a fundamental test of our understanding of how black holes grow and how they shape the environments around them. If these intermediate mass black holes are truly absent, it forces us to reconsider the very physics of dense stellar systems. Perhaps the gravitational dynamics in these clusters are more violent than we thought, ejecting the budding black holes before they can grow. Or maybe their feeding mechanisms are so efficient they leave almost no trace. Each superstar cluster we study in the antennae is a potential hiding place for one of these elusive giants, and every non-detection sharpens the mystery, pushing us to look deeper and think harder about the hidden architecture of the cosmos. The chaotic dance of these galaxies has left its mark deep within their very hearts. At the center of the sprawling wreckage, we find the two original galactic cores, known as NGC 4038 and NGC 4039. They are not the serene, organized centers we might expect. Instead, they are profoundly distorted, bearing the scars of their close encounter. The strangest part is how differently each has reacted to the violence. They are like two survivors of the same disaster, one emerging dazed and quiet, the other lashing out in a furious burst of energy. This asymmetry is a direct testament to the unpredictable chaos of galactic mergers. One nucleus appears to be far more active than the other, its central supermassive black hole likely gorging on a larger share of the gas and dust stirred up by the collision. This frantic feeding can ignite the core, turning it into a powerful engine that can influence its entire surroundings. The other core, by contrast, seems relatively quiescent, perhaps having already consumed the readily available fuel in its vicinity or having its gas supplies stripped away by the gravitational tug of war. This imbalance is not just about the black holes. It ripples outward, affecting the very rhythm of creation around them. The more active core is often surrounded by a more intense firestorm of new star formation, as infalling gas is compressed to its breaking point. The quieter core might be nestled in a region that is, by comparison, a relative lull in the stellar baby boom. Why would two similar galaxies respond so unevenly to the same event? The answer lies in the messy physics of the impact. The angle of their approach, their original rotation speeds, and even slight differences in their initial mass distribution could have conspired to funnel torrents of material toward one black hole while starving the other. It is a cosmic roll of the dice, a reminder that no two collisions are ever truly identical. This lopsided evolution provides a crucial insight. These titanic mergers do not create a single, homogeneous new galaxy, but a patchwork of different environments, each with its own history and its own future, all stitched together by gravity. These galactic winds are so powerful they can blow the future of star formation right out of the galaxy. Rivers of superheated gas are being ejected from the antennae's disks at speeds reaching thousands of kilometers per second. Imagine a hurricane where the winds move at over 2 million miles per hour, a force so immense it can strip a galaxy of its most vital resource. This is not a gentle breeze, but a firestorm of particles blasted into the void. The engine for this incredible exodus is twofold. First, consider the sheer number of supernova explosions occurring in the star-forming frenzy. Each one acts like a cosmic piston, driving powerful shockwaves through the surrounding gas. When you have thousands of these detonations happening in a relatively small volume of space, their collective effect is not just additive, it is multiplicative. The shockwaves merge and reinforce each other, creating a pervasive, high-pressure environment that pushes gas outward. Second, add to this the relentless radiation pressure from the most massive newborn stars. These stellar titans pour out so much ultraviolet light that it physically pushes on the gas around them, like a constant, invisible wind. Together, these forces combine into a feedback loop of staggering violence. The collision makes the stars explode and shine with ferocious intensity, and that collective energy then drives the gas away. The strangeness here is the sheer scale of the loss. These outflows are not minor leaks. They are a fundamental plumbing issue for the entire galactic system. This gas is the raw fuel for the next generation of stars. By blowing it out into intergalactic space, the current frenzy of star formation is essentially sowing the seeds of its own demise. It is a self-regulating and ultimately self-limiting process. The galaxy is effectively turning off its own star-making factory by exhausting the supply line. But this cosmic expulsion is not a total loss. The gas being ejected is not pristine hydrogen and helium. It has been enriched, polluted with the heavy elements forged in the hearts of those short-lived massive stars and scattered by the supernova. Elements like oxygen, carbon, and iron are being carried along for the ride. This means the winds are seeding the vast, empty spaces between galaxies with the very materials needed for planets and life. The Antennae Galaxies are not just colliding, they are bleeding their enriched essence into the cosmic web, contributing to a reservoir that might one day fuel star formation in an entirely different galaxy, far in the future. Surrounding the visible wreckage lies an invisible ocean of fire. A colossal halo of gas, heated to millions of degrees, envelops the entire Antennae system. This is not a gentle warmth, but a superheated plasma corona that stretches far beyond the bright, tangled galaxies we see. Its discovery revealed a component of the merger so vast and energetic it had been hiding in plain sight. The sheer scale of this hot gas halo is difficult to overstate. If you could see its X-ray glow with your own eyes, it would appear larger than the galaxies themselves, a faint, shimmering ghost embracing the chaos within. How did this immense structure come to be? The answer lies in the relentless violence of the collision. Think of the countless supernova explosions and the powerful shockwaves generated as the two galaxies plowed through each other. Each of these events acts like a submerged depth charge in a galactic sea, transferring a colossal amount of energy into the surrounding gas. This energy does not simply dissipate, it accumulates, heating the diffuse hydrogen and helium that fills the space between stars until it glows in the high-energy X-ray part of the spectrum. This is not a gentle simmer, it is a rolling, galaxy-wide boil. The strangest property of this halo is its incredible energy budget. While the brilliant starlight and frantic star formation capture our attention, this diffuse, superheated corona actually contains a significant portion of the entire system's thermal energy. It represents a massive sink, a place where the kinetic violence of the merger has been converted and stored as raw heat on an almost unimaginable scale. For a long time, this component was overlooked, its faint, pervasive glow lost against the brighter, more concentrated sources. Yet it is a fundamental part of the merger's anatomy. This hot gas is a permanent record of the energy released by the collision, a thermal echo of every supernova and every gravitational shock that has rippled through the system. It is a reminder that the true impact of such a cosmic crash extends far beyond the visible debris, inflating a blister of multimillion-degree gas that will linger for eons, long after the new galaxy has settled into a quiet middle age. This cosmic soot is not spread evenly like fine powder. It is a chaotic, clumpy mess, a sprawling tapestry of dark lanes and glowing filaments woven through the wreckage. The dust in the Antennae Galaxies has been violently rearranged, its geometry twisted into forms rarely seen in a solitary spiral. The collision has taken what was once a relatively orderly distribution and thrown it into a state of intricate, beautiful disorder. Imagine the fine, dark flour you might use for baking. In a calm kitchen, it sits in a neat pile. But if you were to slam 2 bags of it together, the powder would erupt into a complex, 3-dimensional cloud with dense clumps, wispy tendrils, and vast empty voids all existing at once. That is the kind of transformation we are witnessing on a galactic scale. The gravitational tides have acted like cosmic hands, kneading and pulling the interstellar dust, while shockwaves from supernova have carved out bubbles and compressed other regions into dense, dark knots. The result is a shadowy architecture that blocks and redirects the light from billions of stars behind it, creating the deep, complex silhouettes we observe. But the strangeness goes deeper than just its shape. The very composition of these dust grains may be changing. As they are blasted by intense radiation from newborn stars and subjected to the immense pressures of colliding gas clouds, their structure can be fundamentally altered. Simple silicate and carbon grains might be shattered into smaller fragments or fused together into larger, more complex aggregates. Some molecules frozen onto their surfaces could be blasted away, while new compounds form in the chaos. This means the dust in the antennae is not a passive spectator. It is an active participant being physically and chemically transformed by the violence around it. This has a direct and profound effect on how we perceive these galaxies. Dust is not neutral. It imprints its own signature on the starlight that passes through. It preferentially scatters blue light and allows redder light to pass, a process called reddening, similar to how our own atmosphere makes the sun look red at sunset. But with dust this clumpy and potentially altered, the effect is uneven and unpredictable. A star that should appear blue might look oddly dim or strangely red because its light has taken a complicated path through this labyrinth of cosmic soot. Astronomers must become detectives, carefully decoding the distorted messages carried by the light to understand the true nature of the stars and gas hidden within. The unusual dust geometry is more than a visual spectacle. It is a dynamic, evolving component of the collision, a filter that both obscures and reveals, constantly remaking itself and the universe we see through it. This frantic starburst phase transforms the Antennae Galaxies into a cosmic engine of creation. We call this a starburst galaxy, a term that perfectly captures the sheer, explosive intensity of its star-forming frenzy. While our own Milky Way gives birth to roughly 1 new star each year, the antennae are producing them at a rate dozens, even hundreds of times faster. It is a temporary but spectacular state, a brilliant flash in the pan on cosmic timescales, and it is all triggered by a single violent event. The galactic collision itself acts as the ultimate spark. Think of the 2 galaxies as 2 immense clouds of gas and stars swinging past each other. Their mutual gravity does not simply pull them together. It acts like a cosmic pair of hands, violently kneading and compressing the vast reservoirs of cold molecular gas that fill their disks. This process funnels unimaginable amounts of this star-forming fuel directly into the central regions, piling it up into dense, turbulent clouds. It is this sudden, extreme concentration of raw material that ignites the firestorm. The gas clouds, crushed under their own enhanced gravity and the external pressure of the collision, can no longer support themselves. They begin to collapse, not in isolated pockets, but in a coordinated, galaxy-wide avalanche of star birth. Entire swaths of the galactic core turn into a single, frantic stellar nursery, operating at maximum capacity. This is not a gentle process. It is a chain reaction of gravitational collapse on an epic scale. The strangeness lies in its temporary nature. A starburst like this cannot last. It is a brilliant but wasteful boom. The very stars it creates so prolifically are the ones that will shut down the factory. The most massive of these new stars live fast and die young, exploding as supernova within just a few million years. Their collective energy, along with the intense radiation from other brilliant newborns, drives powerful galactic winds that blow the remaining gas clean out of the system. The galaxy is essentially consuming its entire future fuel supply in one glorious, unsustainable burst. For a short while, the Antennae Galaxies shine with an incredible brilliance, but they are also ensuring that this era of hyperactivity will inevitably sputter out, leaving behind a galaxy rich with mature stars but starved of the gas needed to make new ones. This orderly rotation has been shattered. The beautiful, predictable spiral arms of the original galaxies are gone, and with them, the graceful orbital dance of their stars. Each of the billions of suns within this collision has been given a new, chaotic set of instructions by gravity's invisible hand. Picture our own solar system's nearly circular path around the Milky Way, a stable loop repeated every 250 million years. Now, throw that clockwork precision into a cosmic blender. Stars in the antennae are now tracing wildly elliptical paths, plunging from the distant outskirts on a long, slow fall inward, only to whip around the galactic core at incredible speeds and be flung back out again. It is a gravitational roller coaster on an unimaginable scale, a system where stable orbits have become a relic of the past. This kinematic upheaval is the true signature of the merger, written in the motion of every star. The strange phenomenon is this complete rewriting of the stellar rulebook. The galaxies are losing their identity, transforming from two distinct, rotating disks into a single, messy, and dynamically hot system. The stars are no longer citizens of an orderly spiral metropolis. They have become a frenzied swarm, their collective paths weaving a three-dimensional tangle that defies simple classification. This chaos is not just for show, it has profound consequences. These erratic stellar paths prevent the new galaxy from settling back into a neat disk. The constant, cross-cutting orbits act like a stabilizing force, ensuring the merged entity will likely become an elliptical galaxy, a featureless ball of stars without spiral structure. The kinematic information is a fossil record of the impact itself. By tracing the paths of these stars backwards, astronomers can recreate the exact moment of the collision, understanding the angles and speeds that led to this beautiful, star-shattering chaos. At the very heart of the collision, where the two galactic disks are physically interpenetrating, lies a region of almost unimaginable violence. This is the overlap zone, the true epicenter of the entire cosmic crash. Here, the gas clouds from the two galaxies are not just being nudged by gravity, they are slamming into each other head-on at phenomenal speeds. Picture two weather systems on a continental scale colliding, but instead of producing a simple storm, the impact forges a hurricane of starburst so intense it defies simple description. The compression is instantaneous and catastrophic. Immense clouds of hydrogen gas, each light years across, are rammed together, creating shock fronts of unbelievable pressure that trigger gravitational collapse on an industrial scale. The star formation here is not just rapid, it is extreme and bewilderingly complex. We see not just superstar clusters, but what might be hyperstar clusters, structures so young, dense, and brilliant they push the limits of what we thought was possible for a single stellar nursery. This frantic creation may also be unlocking a deeper power. All this chaotic infalling gas is not just making stars. A significant portion of it is likely being funneled directly toward the supermassive black holes hiding within the galactic cores. The overlap region could be the very trigger that ignites a quasar. turning one or both of these black holes into the most luminous objects in the universe for a short, spectacular time. This would be a brief but phenomenal flash, a beacon of light powered by the final death screams of gas clouds torn apart in the collision. And the chemical conditions in this crucible are unlike anywhere else. The constant bombardment of shockwaves from colliding clouds and the intense radiation from countless newborn stars create a pressure cooker for molecular chemistry. Here, simple atoms are fused into complex molecules under conditions so unique they could be seeding this region with a specific, and potentially rare, cocktail of elements and compounds. The overlap is more than just a messy intersection. It is a unique cosmic laboratory where the most violent processes of a galactic merger are concentrated into one searingly bright and mysterious point. These chaotic stellar nurseries are also producing some of the most extreme stars in the known universe. Deep within the Antennae's bright clusters, we find Wolf-Rayet stars, stellar monsters that burn at temperatures so high they glow with a searing, electric blue light. Their lives are a frantic race against time. A typical Wolf-Rayet star is the exposed core of a star that was originally dozens of times more massive than our Sun. It has already burned through its hydrogen fuel and is now fusing heavier elements in its core, all while being stripped bare by its own incredible power. The defining strangeness of these stars is their phenomenal stellar winds. They do not simply shine, they evaporate. These stars blast their own outer layers into space at speeds exceeding thousands of kilometers per second, creating a constant, supersonic gale of charged particles. This is not a gentle breeze, but a hurricane of star stuff so powerful it can completely reshape its surroundings. Imagine a single star so forceful that its wind carves a vast, empty cavity in the surrounding nebula, a bubble of cleared space that can be dozens of light years across. Inside this bubble, the gas is heated to millions of degrees and glows with an intense, harsh light. The energy output is staggering. A single Wolf-Rayet star can pour more energy into its local environment through its wind than an entire cluster of normal stars. This makes them the dominant players in the feedback cycle within the Antennae's star-forming regions. They are the ultimate cosmic landscapers, using their ferocious winds to blow away the very gas clouds that gave them birth, simultaneously shutting down star formation in their immediate vicinity while compressing the gas at the edges of their bubbles, potentially triggering the next round of starbirth elsewhere. Their presence is a brilliant, fleeting signal, because they represent such a late and volatile stage in a massive star's life. A Wolf-Rayet star can only exist for a few 100,000 years before it explodes as a supernova. Spotting them is like finding a lit firework fuse. It is a guarantee of spectacular, imminent destruction. Each one we identify in the antennae is a direct timestamp, a sign that a furious burst of star formation happened here, and only very recently. They are the frantic, brilliant heartbeat of the collision, living fast, dying young, and forever changing the chaotic world that made them. Threading through the chaos of the antennae is a ghostly circulatory system, a vast network of faint, glowing filaments visible only in specific wavelengths of light. This is the diffuse ionized gas, a sprawling web of hydrogen that has been supercharged by the relentless ultraviolet radiation pouring from the galaxy's countless massive stars. That intense light is so powerful it strips electrons from the hydrogen atoms, leaving behind a plasma that glows with a soft, ethereal light. The strange beauty lies in the intricate, thread-like structure of this gas. It does not form a uniform fog, but instead traces delicate, looping pathways and vast, arching bubbles that stretch for thousands of light years. These filaments are like cosmic wiring, mapping the paths of energy as it escapes from the frantic star-forming regions and bleeds out into the wider galactic environment. Imagine a sponge soaked in luminous fluid, its complex internal structure suddenly made visible. That is what we are seeing, the architecture of empty space itself, outlined by this escaping energy. Each glowing thread tells a story of a stellar nursery's influence, a direct channel through which the fury of newborn stars is conducted far beyond their local neighborhood. This network reveals a hidden level of organization within the apparent chaos, showing how energy from the most violent places is distributed, shaping the entire galactic ecosystem. It is a permanent, glowing record of the stellar winds and radiation that are both building and tearing apart the Antennae Galaxies from the inside out. This silent, final act is already written into the gravitational code of the Antennae Galaxies. The two supermassive black holes, each millions of times heavier than our Sun and currently separated by about 1,000 light years, are destined for a confrontation of cosmic proportions. Right now, they are like two monarchs presiding over their own turbulent kingdoms, but the dance of the merger is slowly drawing them together. As the surrounding stars and gas interact and lose energy through a process called dynamical friction, these black holes will begin to sink, spiraling ever closer toward the shared center of the new, combined galaxy. They will eventually form a tight binary system, a black hole pair locked in a final, intimate waltz. The strangest part of this entire saga is this inevitable future, a cataclysm that has not yet happened but which the laws of physics demand. When they finally merge, the event will be one of the most violent the universe can produce. As they inspiral in the last few moments, they will stir the very fabric of space-time, sending out ripples known as gravitational waves. These are not waves of light or sound, but literal distortions in the geometry of the cosmos, stretches and squeezes in the distance between everything. The energy released in that final fraction of a second will be beyond comprehension, briefly outshining the combined light of every star in the observable universe. Yet this radiance would be entirely invisible to our eyes, a silent, shivering tremor in the dark. For a moment, the merged galaxy would sit at the center of a ringing cosmos. A bell struck so hard its vibration would travel for millions of light years. We are not yet capable of detecting such an event from the antennae, as the frequency of these waves would be too low for our current observatories. But future space-based gravitational wave detectors are being designed to listen for exactly this kind of colossal merger. The antennae system offers us a preview, a living blueprint of a process that was common in the early universe but is now a rare spectacle. We are witnessing the prelude to a space-time earthquake, watching the setup for a blast whose echo we hope to hear in the distant future. The chemical map of the Antennae Galaxies is a messy, unpredictable patchwork. While we might expect the heavy elements forged in supernova to spread evenly, like food coloring stirred into water, the reality is far more chaotic. Some regions shine with the strong spectral lines of oxygen, carbon, and iron, elements that are the unmistakable signature of prior stellar generations. Yet, right next door, astronomers find pockets of gas that are surprisingly pristine, composed almost entirely of the primordial hydrogen and helium that date back to the Big Bang. This uneven distribution is a strange and crucial clue, a chemical fossil record written across the galactic wreckage. The reason for this patchiness lies in the violent and inefficient nature of the mixing process itself. When a supernova explodes, it does not gently disperse its enriched contents. It blasts them out in a powerful, directional shockwave, a cosmic cannon that fires heavy elements into specific corridors of space. This creates localized bubbles of highly enriched material, while leaving other vast regions of gas untouched and chemically primitive. Stellar winds from massive Wolf-Rayet stars act in a similar way, carving out cavities and spraying their own unique blend of processed elements onto their immediate surroundings. The galactic collision makes this mixing even more challenging. The turbulence and gravitational chaos prevent the galaxy from settling into a state of equilibrium. There is no gentle, galaxy-wide stir to homogenize the brew. Instead, you have these isolated chemical factories operating independently, their products not yet blended into a uniform mixture. This tells a complex, layered history of star formation. A region rich in oxygen might pinpoint the location of a past supernova cluster that has since dispersed. An area with a specific ratio of carbon to iron could reveal the dominance of a particular type of stellar death. By reading this chemical map, astronomers can trace the bursts and lulls of the starburst, understanding not just where stars are being born today, but where they lived and died millions of years ago. The galaxy's past is literally written in the uneven chemistry of its gas, a story of creation and pollution that is still being assembled. Even the most violent explosions can leave behind a ghostly whisper long after the initial flash has faded. Wrapped within the antennae's chaotic glow, astronomers hunt for something far more subtle than the brilliant stardust and colliding gas clouds. They search for light echoes. These are not sounds, but a cosmic mirage, a delayed replay of ancient cataclysms written in photons. Here is how it works. When a supernova explodes, it unleashes a tremendous pulse of light in all directions, a flash that travels outward at the ultimate speed. Most of that light travels directly toward us, announcing the star's death across the light years. But some of that initial flash travels on a different path, striking vast, dark clouds of dust that float in the galactic outskirts. This dust does not absorb the light permanently. It acts like a colossal mirror, scattering the photons and sending them on a new, longer journey to our telescopes. That means we see the supernova twice, first from the direct path, and then, hundreds or even thousands of years later, we see its echo as the reflected light finally arrives. We are essentially watching a recording of a stellar death that happened long ago, a recording that has been bouncing around the galaxy's dusty halls. The strangeness is profound. It allows us to witness the same explosion across multiple points in time. By studying the spectrum of this echoed light, we can analyze the chemical composition of that ancient supernova, just as if it had happened yesterday, peeling back the layers of the star to understand its final moments. These faint, shimmering rings or arcs of light are more than just pretty relics. They are a form of time travel, giving us a second chance to observe and learn from cosmic events that should have been lost to history. In the Antennae Galaxies, with their epidemic of supernova, the opportunities to catch these echoes are greater than almost anywhere else. Each one is a message in a bottle, sent not across the ocean, but across the centuries, carrying the final secrets of a star that died when the collision was still in its earliest, most violent stages. Deep within the wreckage, an invisible force is being violently rewired. The colossal collision is not just reshaping stars and gas. It is twisting and amplifying the galaxy's magnetic fields into new and strange configurations. Think of the original magnetic fields of the two galaxies as two separate pots of magnetic fluid, each with its own gentle, internal flow. Now, slam those pots together and stir them with unimaginable force. The gravitational turmoil of the merger acts as that cosmic spoon, churning the interstellar medium and stretching the magnetic field lines, wrapping them around the colliding gas clouds and pulling them into intricate, chaotic knots. This process can dramatically intensify the field's strength, turning a faint background presence into a powerful, dynamic actor in the drama. The strangest outcome of this reconfiguration may be its paradoxical sense of order. Amidst the chaos, astronomers predict the emergence of highly organized magnetic fields, particularly within the vast, sweeping tidal tails. As gas and dust are drawn out into these long streamers, the magnetic field lines could be stretched and combed straight, aligning into surprisingly uniform patterns across hundreds of thousands of light years. It would be like combing tangled hair, transforming a mess into smooth, parallel strands. In other regions, the opposite occurs, with the field intensifying into incredibly powerful, localized knots. These magnetic fortresses can have a profound influence on their surroundings. They can act as cages for high-energy cosmic rays, trapping these charged particles and preventing them from escaping, which in turn affects how these rays travel through the galaxy. They can also influence the very birth of stars. A strong, turbulent magnetic field exerts pressure on a collapsing cloud of gas, providing support against gravity and potentially slowing or even halting the formation of new stars. In this way, the invisible magnetic architecture, forged in the collision, becomes a silent architect, its hidden hands guiding the flow of energy and the rhythm of creation itself across the ruined galaxies. This celestial fireworks display never truly stops, for the Antennae Galaxies are a stage for countless transient events, unpredictable performances that flare into view and vanish just as quickly. Beyond the grand, slow-moving drama of the collision, there is a layer of rapid, fleeting chaos, a population of objects that appear, change, and disappear on human timescales. These are the transient and variable objects, the quick, bright flashes in the cosmic pan that make the antennae a uniquely dynamic target. Nova are one such event, occurring in binary star systems where a white dwarf, a dense stellar corpse, steals gas from its companion. This stolen hydrogen piles up on the white dwarf's surface until it ignites in a runaway thermonuclear explosion. The star can suddenly brighten by tens of thousands of times, becoming a brilliant new point of light for a few days or weeks before fading back into obscurity. In the crowded stellar metropolises of the antennae, such events are likely common, each one a brief, violent flare signaling a stellar partnership pushed to its limit. Then there are the flaring stars themselves, young, magnetically hyperactive stars that can unleash colossal eruptions, doubling their brightness in mere hours as magnetic field lines snap and reconnect in their atmospheres. It is a constant, low-level crackle of stellar lightning, a reminder that even single stars can be wildly unpredictable. Perhaps the most elusive of these phenomena are microlensing events. These are not changes in a star's intrinsic light, but rather cosmic illusions. When a dark, compact object like a solitary black hole or a neutron star drifts precisely in front of a more distant background star, its gravity acts as a tiny lens, bending and focusing the background star's light. For a few days or weeks, the background star appears to mysteriously brighten and then fade without any change in its color. A perfect, temporary mirage created by gravity's invisible hand. The strangeness lies in this ever-changing landscape. If you could monitor the antennae with a time-lapse camera, you would see a field of view that flickers and pulses with these transient events. A celestial canvas where new points of light ignite and old ones vanish. Each unpredictable flash is a clue, a brief window into processes that are otherwise invisible, from the secret lives of binary stars to the silent drift of dark, massive objects through the galactic wreckage. This constant state of flux makes the antennae not just a static object of study, but a living, breathing cosmic laboratory where the only constant is change itself. All that scattered dust holds the blueprint for entire worlds. Within the sprawling debris of the Antennae Galaxies, trillions of tons of fine, rocky, and carbon-rich particles are being cast adrift. A cosmic silt forged in stellar furnaces and scattered by titanic explosions. This is not mere dirt. It is the primal clay from which planets are born. In the quieter epochs that will follow this collision, this dust will begin to settle, coalescing within the disks of gas that swirl around newborn stars. Microscopic grains will stick together, forming pebbles, then rocks, then planetesimals, in a slow, gravitational dance that builds planets from the ground up. The profound strangeness is the dual nature of this violence. The same catastrophic event that tears apart the galactic order on a grand scale is simultaneously manufacturing the very ingredients for cosmic rebirth on a smaller, more intimate one. The heavy elements so critical for this process, the silicon for rocks, the oxygen for water, the carbon for complex chemistry, are all being produced in the supernova blasts and stellar winds that rage throughout the merger. Without this violent enrichment, the future planetary systems would be barren, consisting only of gas giants or icy bodies. But here, The dust is pre-polluted with the elements of life. A future planet forming from this material might be born with a rich, metallic core and a mantle full of radioactive elements to keep its interior warm, setting the stage for plate tectonics and a protective magnetic field. Its crust could be seeded from the start with water ice and complex organic molecules, the same kinds we see in the unidentified infrared features. The collision is essentially performing galactic-scale terraforming, not on a single world, but on an entire future generation of solar systems. It ensures that the planets that eventually form will be rocky, complex, and chemically primed for possibility. So while we witness the death of two galaxies as we knew them, we are also looking at the genesis of untold millions of new worlds, each one a potential cradle for whatever comes next. Even our most powerful supercomputer simulations are being challenged by the reality of this collision. The Antennae Galaxies act as a cosmic benchmark, a real-world experiment against which we test our virtual models of galactic evolution. Scientists program the laws of physics into these digital universes, setting in motion two spiral galaxies on a collision course governed by gravity, gas dynamics, and dark matter. They run the simulation forward millions of years, watching as the digital galaxies merge, expecting to see a perfect replica of the antennae we observe. Yet sometimes, the virtual universe and the real one do not align. Strange discrepancies emerge, small but crucial differences that force a fundamental rethinking of the underlying physics. Perhaps the simulated starburst is too intense and burns out too quickly, or the distribution of newly formed superstar clusters does not match the observed, messy reality. Maybe the dark matter halos in the simulation behave a bit too smoothly, failing to capture the subtle gravitational quirks revealed by lensing studies. Each mismatch is a gift, a clear signpost pointing toward a gap in our knowledge. It forces astronomers to ask difficult questions. Are we properly accounting for the complex feedback from supernova and stellar winds, processes that can blow gas away and shut down star formation in ways we do not fully understand? Is our model for the mysterious nature of dark matter itself too simple? The Antennae Galaxies, in all their beautiful complexity, are essentially telling the simulations they are not quite right. This is not a failure of science, but its very engine. Every discrepancy drives a new cycle of refinement, where theorists tweak their code, add new physical processes, and run the simulation again, inching closer to a model that can truly capture the chaotic, creative, and strange reality of two galaxies becoming one. Buried within the dusty heart of the collision, countless pinpricks of infrared light defy our gaze. These are the unresolved compact infrared sources, myriad points of intense energy swallowed by the very cosmic soot they illuminate. Each one is a brilliant mystery, a power source whose true identity is veiled behind thick curtains of dust that block our visible light telescopes. Their glow is the thermal signature of immense heat, the kind generated by ferocious stellar birth or the violent feasting of black holes, but the details are frustratingly blurred. One of these tiny, bright dots could be an infant superstar cluster, a stellar metropolis so young its stars are still swaddled in their natal cocoon of gas and dust, their collective light absorbed and re-radiated as this warm infrared hum. Another might be a single, colossal protostar in its final, violent collapse, a sun in the act of being born on a scale so grand it outshines entire star systems. Or, most intriguingly, one of these specks could be the hidden engine of an active galactic nucleus, a supermassive black hole whose bright accretion disk is completely shrouded from our view, its presence betrayed only by the heat its feeding frenzy radiates into the surrounding dust. The strangeness is in this profound obscurity. We know these objects are pouring out tremendous energy, shaping their local environments, and contributing to the galactic firestorm. Yet we cannot tell the difference between a nursery for a million stars and the single, brilliant beacon of a hidden quasar. They are cosmic riddles written in the language of heat, forcing us to use indirect methods and clever deductions to guess at the colossal forces at work behind the dusty veil. These invisible tsunamis ripple across the galactic landscape, born from the most violent forces the collision can muster. When entire clouds of interstellar gas slam into each other, or when a supernova unleashes its raw power, the energy does not simply vanish, it propagates outward as immense shock fronts. These are sonic booms on a cosmic scale, waves of compressed energy traveling at thousands of kilometers per second through the thin medium between the stars. If you could see them, they would appear as vast, rolling walls of force, sweeping up everything in their path. The sheer power behind these shocks is difficult to fathom, capable of heating diffused gas from a few degrees above absolute zero to millions of degrees in an instant. This superheated plasma then glows fiercely in high-energy X-rays, painting the shock fronts as delicate, filamentary structures in satellite observations. But the strangest effect is their dual nature, their ability to both destroy and create in the same breath. A passing shock front can obliterate a quiet, stable cloud of gas, tearing it apart. Yet, when that same wave encounters a slightly denser, colder pocket of hydrogen, it does the opposite. The shock's immense pressure acts like a cosmic hammer blow, violently compressing the gas and nudging it over the critical threshold where its own gravity takes over. This triggers a sudden, forced collapse, igniting the birth of a new generation of stars. It is a relentless cycle, where the death of one stellar family powers the chaotic birth of the next. These spectacular filaments, visible in both X-ray and radio light, are the permanent scars of this process, the ghostly imprints of energy that has sculpted the galaxy, leaving behind both brilliant new suns and vast bubbles of multimillion-degree emptiness. This brilliant firestorm of creation cannot burn forever. The very forces that ignite the stars are the same ones destined to snuff out the flames, a cosmic balancing act playing out in real time. We call this process feedback and quenching, and the Antennae Galaxies are a living textbook on this violent cycle. Feedback is the galaxy's own self-regulating mechanism, a set of powerful brakes applied by the newborn stars themselves. Every supernova explosion and every howling stellar wind from a massive star pumps immense energy back into the surrounding gas. This energy does not just fade away, it heats the gas to extreme temperatures, making it too energetic to collapse and form new stars, and it drives those powerful galactic winds that physically blow the gas reservoir out into intergalactic space. Think of a bonfire so fierce that its own heat and winds scatter the remaining pile of wood, preventing the fire from growing any larger. That is feedback in action. The strange and complex phenomenon here is witnessing the entire life cycle of a starburst, from ignition to its inevitable suppression. We are watching the galaxy sow the seeds of its own decline. This is the quenching phase, the point where the star-forming frenzy essentially chokes on its own exhaust. The galaxy's primary fuel, that cold molecular gas, is either heated into an unusable state or ejected entirely. The brilliant maternity wards begin to shut down, not for a lack of will, but for a lack of raw material. What makes the antennae so fascinating is the uncertainty of the final outcome. Will the quenching be total and permanent, leaving behind a red and dead galaxy full of aging stars? Or will it be a temporary pause, with some of that ejected gas eventually cooling and falling back in billions of years from now, sparking a more gentle era of star formation? The fate of this merged galaxy hinges on this delicate, violent interplay. A battle between creation and destruction waged across thousands of light years. This chaotic dance of creation and destruction is writing the final chapter for two distinct galaxies. The beautiful wreckage we witness today is a fleeting state, a temporary and turbulent adolescence on the path to something far more permanent and serene. The ultimate destiny of the Antennae system is to become a single, massive elliptical galaxy, a smooth, featureless island of stars. This is the 30th and final profound strangeness. the realization that we are watching the violent, messy birth of a galaxy type that is common in the universe today. We are being given a live-action preview of a process that fundamentally shaped cosmic history. Most of the large galaxies we see in the nearby universe are these quiet, red, elliptical giants. For a long time, their origin was a mystery. How did these vast, ball-shaped collections of stars, devoid of spiral arms and active star formation, come to be? The antennae provide the definitive answer. They are the missing link, caught in the act of transformation. The frantic starburst, the galactic winds, and the chaotic stellar orbits are all part of a single, irreversible recipe. The merger process stirs the stars into their randomized, swarming paths, erasing any memory of the original disk structures forever. The feedback from countless supernovae then blows away or heats up the remaining gas, quenching the star-forming fires. What will be left is a galaxy dominated by older, redder stars, a system that has consumed its youth in one glorious, unsustainable burst. The profound thought is that every giant elliptical galaxy we see, every smooth, golden-hued orb in the cosmos, was likely once a scene of beautiful violence just like this. They are the silent, aging adults who were once wild, colliding teenagers. The Antennae Galaxies are not just a spectacle, they are a prophecy written in starlight and fire, showing us how the universe forges its most common islands of stars through the most extraordinary of means. From the impossible light of hidden black holes to the final, silent merger of spacetime itself, we have journeyed through 30 cosmic wonders locked within this single collision. The Antennae Galaxies are far more than a distant spectacle. They are a living laboratory where the universe tests its own most extreme laws. Every strange phenomenon, from the self-destructive tantrums of giant stars to the ghostly whispers of dark matter, reveals a cosmos in constant, violent flux. It is a reminder that creation and destruction are two sides of the same coin, playing out on a stage of unimaginable scale. This is not a static universe, but a dynamic and evolving one, where even the grandest structures are temporary and beauty is born from chaos. So the next time you look up at the night sky, remember the incredible dance unfolding millions of light years away. Let it fill you with a sense of wonder for the hidden forces shaping everything we see. We would love to hear which of these 30 mysteries captured your imagination the most. Was it the stellar cities being built and torn apart, the invisible dark matter shaping the wreckage, or the future planets being seeded in the chaos? Share your thoughts in the comments below and keep looking up.